to expect from the test. Take this one first. Then I have a practice test. So here is the practice test. I have solutions to the practice test. So that's these guys here. I have the formula sheet for the practice test. It should be the same as the formula sheet for the actual test. And lastly, I have the handouts for the section we're covering in class today. So again, a lot of handouts. It's basically everything. Hopefully, you should need to prepare for the test next week. Yeah, sorry, I was going to say, between the two practice tests, the title looks the same. One you'll see has blanks, the other one has answers. I forgot to change the title when I add the answers, so make sure they are two different. One has no answers, the other one has answers. So make sure you know what, you get both of them. One is 3 pages, the other one's 5 pages. What is up with this display? For whatever reason, this projector keeps turning itself off as soon as I start teaching. I don't know why. Okay. Just a couple of things I want to mention as this projector is warming up, if everyone could concentrate. So the first thing is, again, the test is a week from today. On July 22nd. One thing to mention, I will not be here on Thursday's class. I'm actually getting married on Saturday, and there's enough stuff going on this week. There is no way I can make the class on Thursday, so... yeah, anyways, thank you everyone. I'm way too busy this week. So that's why I have this stuff all for you now, is because I know there's not going to be any time for me in the rest of the week to do stuff. I'm not going on a honeymoon immediately, I'm going on a honeymoon after our exams. So I will be back on Monday. I will be checking my work email and I'll be replying to any last minute emails about things. So if you do have any questions, please send me an email. I will definitely get back to you by Monday. Well, Sunday might also happen. I'm not going to make any guarantees about replying to emails on Sunday, but definitely on Monday I will reply to any emails I have then. But yeah, Wednesday, Thursday, Friday this week I'm going to be busy, way busy doing wedding prep stuff. Anyways, and Terry is going to be teaching on this class on Thursday. So there will be class on Thursday. He's going to be starting the Chapter 11 material, which is not on the test. And what else was I going to say? So that's why I'm giving you all this stuff now. Yes?
Are we turning in our assignment 4 on Thursday?
No, assignment 4 is due Thursday, July 24th. I pushed it back till after the test because there's, again, this is one of the thing when I said I'm pushing everything back. I pushed this one back to be due then. Annoyingly, there's only 2 days between the test and it, so it might be a good idea to get started on it before the test. It's definitely is not as long as the last one is. So it's definitely very possible to get it done in these 2 days if you want, but yeah. So this is when the assignment 4 is due. Oh! Either I forgot to print assignment 4, or it's sitting up in the... Anyways, I'll check on the break. I'll check if assignment number 4 is still in the photocopy room. I may have forgotten to wait for it to print. I thought I printed it, but I may have forgotten to print it. Anyways, either way, it is ready. I made it up this morning. It will definitely be on my UFE this afternoon. Why is this still not... Okay. So basically the agenda for today's class is that I'm basically going to finish the rest of the material in Chapter 9. Chapter 9 is on differential equations. Again, we're not going into it in very much depth, but there is sort of more stuff from Section 9.3 and 9.4 that I am going to cover, and that is going to be on the test. So again, I didn't have time to collect Money's point cards last class. There are no Money's points. Because of this, there's going to be lots of problems to do group problems at the end. Lots of time to do group problems at the end. So yeah, I'm going to go through sections 9.3 and 9.4, and then we'll have group problems at the end of the class. That's basically the plan for today's class. During the break, I'm going to be running upstairs to get those assignment number 4s ready, so I'll probably hand back the quizzes later during the group problem section. But I want to make sure you got the paper for assignment 4 before anything else happens. Okay. So any questions about the agenda for today's class? Any questions about the test next week? The fact that I won't be here on Thursday. Yes?
Who's teaching Thursday?
Terry.
Terry?
Yeah. Terry. Narudin. Yeah, exactly. I was trying to remember how to spell his name. N-U-R-U-T-A-R-I-Q. His last name is N. I think it's spelled like that. I think it's 1 R and 2 E's, but I could be misspelling it.
Is he a good guy? Like, bro?
Yeah. Yes. Anyways, I don't know. To be honest, I don't. I've actually. It's one of these funny things. Of course, we never get to see each other teach, so I can't actually say at all what he's like as a teacher. But yeah. Yeah. Anyways, I know he also. Yeah. Exactly.
Tell him, did you get my email?
Yes.
Okay.
I have not had a chance to pass it on to the class, but thank you so much for sending that.
Yeah.
Anyways, Daryl sent me a graphing calculator program for doing like all the approximations we've learned. Midpoint rule, Simpson's rule, trapezoid rule. I'm totally going to pass it on to the class.
All in one.
Yeah.
I made it from scratch. So
Thank you so much for doing that. I was going to say, like... Yeah. Yeah. No, that's great, because I'm sure... I don't know how much work it required, I'm not. But yeah, probably a fair bit, so... Yeah. Okay. Any other questions before I move on to... Oh, the other thing to mention, there's not going to be a WebAssign quiz till after the test. So the next WebAssign quiz will be due like the July 29th. So don't worry about. There will be WebAssign like homework assignments for these sections I'm covering today. You can use them to help prepare for the test, but you're not going to have a quiz on that stuff. A WebAssign quiz till afterwards.
Well, no, it's the,
Okay, if there's no other questions, I'm going to continue from where I left off. So, if you remember what I talked about in section 9.3.1, I talked about this thing which is called separable differential equations. And a separable differential equation is one where you can rearrange it to get all the x's on one side, all the y's on the other side, and then you can integrate both sides. And that'll allow you to solve the differential equation. That'll allow you to find all the functions which are solutions to that differential equation. Now, the next thing I'm going to be talking about is what are called separable initial value problems. And if you remember, an initial value problem is a differential equation together with what's called an initial condition, which is basically a starting point. So the differential equation sort of describes how the thing in question changes. The initial condition describes where you do start from. Solving a separable initial value problem is only a little bit more difficult than solving a differential equation. The same technique of separating variables is still going to apply. We get all the x's on one side, all the y's on the other, integrate both sides. The only difference is when we integrate both sides, we get this constant c in there, right? When you integrate something, you always have that plus c. The initial condition is going to allow you to figure out what the c actually is. So once you've integrated both sides, you've got that plus c in there, we figure out what the initial condition is and use that, plug that into the equation in order to solve for c. And that'll basically tell you exactly what the function is. That constant plus c will actually become an actual specific number. So to see an example of what I'm going to do example 3 here. So here we have y prime equals xy sine x over y plus 1. Right, so this is a relationship between y prime, x, and y. So it's a differential equation, right? And it's got this thing called an initial condition, which just says y of 0 is 1, which means when x is 0, y is 1. So if we want to solve this thing, our goal is always to be able to get all the y's on the left, keep all the x's on the right. So I'm going to start by multiplying both sides by y plus 1, divide both sides by y. So we get something that looks like that. Y plus 1 times y prime over y equals x sine x. The other thing to mention is y prime I can write as dy over dx. And this dx is sort of like an x, so I want to move the dx over here. So if I multiply both sides by dx, I get x sine x dx on the right-hand side. And on the left-hand side, I have y plus 1 over y dy. And now, I can put an integral sign on both sides. Integrate this side, integrate this side. So once you've gotten all the y's, including the dy on one side, all the x's, including the dx on the other, you're allowed to integrate both sides. Again, you can sort of think about this thing, this equation, without the integral signs as sort of like a substitution type equation. Putting integral signs is just sort of saying we're just doing the substitution to this thing to get this thing, or something like that. So next we have to actually do these integrals. So if you look at this left-hand side, we have y plus 1 over y dy. Y plus 1 over y simplifies to 1 plus 1 over y. Now here, to integrate x sine x, we have a product of a polynomial function and a trigonometric function. That's something we've got to do with integration by parts. So my u here is going to be x. My dv is going to be sine x dx. So if u is x, du is dx, and dv is this, v is the antiderivative, which is negative cos x. So on the right-hand side, we'll get u times v, which is going to be negative x cosine x. I mean, my u times my v is negative cosine x, and my u is x, minus the integral of v, which is negative cosine x, du, which is dx. Now to keep going, we integrate this, we integrate this. So if we have to take the antiderivative of 1, we get y. Take the antiderivative of 1 over y, we get ln of the absolute value of y. On the right-hand side, this negative x cosine x isn't going to change. These two negatives will become a positive. The antiderivative of cosine x is sine x. And then we have a plus c, because there's always a constant of integration. So here we've gone from a differential equation to a normal equation, right? This is a solution to that differential equation. This is a sort of a description of a function. Now the problem with this description of a function is we don't have y in terms of x. We have y plus ln absolute value of y on the left-hand side. And this is an example of one where we can't really rearrange this to solve for y. If we just had the y, that would be easy. If we just had the ln absolute value of y, that would be easy. Because we have both, we can't really do anything there. So this is what we call an implicit solution. It's an equation rather than a function. It's written as an equation, but it still sort of is a description of a function. It's a description of a graph. Right? This equation does have a graph, and that graph is a solution to this guy. And we can't rearrange it to solve it for y. We can't rearrange it to write it as y equals f of x, but we still have that solution. So the next thing we need to do is we need to take that solution, and we need to actually plug in the initial condition. So the initial condition here is that y of 0 equals 1. So that's saying when x is 0, y is 1. So every time we see a y, we put in 1. Every time we see an x, we put in 0. I'm just going to write it this way. Y equals 1, x equals 0. So y becomes 1. Ln absolute value of y becomes ln absolute value of 1. X becomes 0. Plus sine 0 plus c. So 0 cosine 0 is just 0. Sine of 0 is just 0. Ln of 1 is just 0. So we get that 1 equals c. So the final solution is an implicit solution. And the implicit solution looks like y plus ln absolute value of y equals x. Oh, negative x cosine x plus sine x plus 1. Again, we know c equals 1. So that's the solution. Again, you look at the solution, it's not an actual explicit solution. It doesn't say specifically, what y is in terms of x. But it's still an equation relating y and x. It's still a solution to that initial value problem, just called an implicit solution. Yes?
Where did the initial dx come from? You got a dy and dy over dx. That's fun.
Y prime is dy over dx. That's what y prime is, right?
Right.
Now, again, this is, I was going to say, Daryl mentioned earlier that, like, when you originally used the symbol dy over dx for y prime, you said, okay, the dy over dx can't be separated. Later on, you may have learned in Calculus 1 what the dy and the dx actually represent. And it turns out that the derivative, dy over dx, is the same thing as the ratio between dy and dx. So you can sort of move the dx over here and separate the two. But yeah, y prime is also known as dy over dx. Two different ways of writing the same thing. That's the same reason that when you have like u equals x squared, du over dx is 2x, so du is 2x dx. Right, we're just taking the derivative and then we're moving the dx to the other side. It's the same thing we're doing when we're doing substitution. We write it as a derivative and then move the dx to the other side. Yeah. Okay. Oh yes, sorry.
Because it's still technically correct to write the plus c on the y half of the equation, would you get another correct answer as negative 1?
So if you put a plus c over here, what would happen is you'd get 1 plus c equals 0, so c would be negative 1. And you get the same thing here, except rather than having a plus 1 on this side, you have a minus 1 on this side. Two different equations which have the same graph. Right? Two different ways of describing the same implicit function. That's the idea. So yes, that would totally be fine. Usually, I don't know why we always put it on the x side. I mean, I guess it usually makes it easier because you're always trying to solve for y. So if the c over here, it's going to be easier to solve for y than for the c over here. But, yeah. So, example 4 is the next one I'm going to do. So here we have capital L over dt equals k L squared ln t, and L of 1 equals negative 1. So here, rather than the variables being L and x, the variables being y and x, the variables are L and t, capital L and t. One thing to mention is k here is not one of the variables. That k here is a constant. So it's important to keep that in mind. If you see a dl over dt here, the L is a dependent variable, it's like the y. The t is the independent variable, it's like the x. The k is neither of those, so it's just a constant. So, we need to now rearrange this to get all the l's on one side and all the t's on the other. So I'm going to divide both sides by L squared, multiply both sides by dt. So we'll get dl over L squared equals k ln t dt. So next step, we can put an integral sign over on both sides. When we put an integral sign here, we notice that L squared on the bottom is the same thing as L to the negative 2. And the k on this side can be pulled out front of the integral sign over here. So we get something that looks like that. Now, we want to integrate both sides. So if we integrate this guy, the antiderivative of L into the negative 2 is L to the negative 1 over negative 1. Here, the k is going to stay. When we take the antiderivative of ln(t), we can do it by integration by parts if you want, or you can just memorize the antiderivative of ln(t). The antiderivative of ln(t) is t ln t minus t. And I'm going to put a plus c out here. Now, if you wanted to, you could put the plus c inside the brackets. It doesn't really matter. But I'm going to put the plus c outside to make things a little bit easier. Next, I'm going to... Oh, yes, sorry.
Does it matter where the k goes to that side or this side?
Yes, because if the k goes inside, it should go in here, and it should also go on here.
The other side of the equation.
Oh, here. Oh, if you move it to the other side of the equation. No, it does not. That'll give you the same answer in the end, either way. Yeah, if the k was over here, you'd have... The c would be a different c, but the final answer would still be the same, if that makes sense. Yeah. So yeah, but you could move the k over here. That wouldn't be a problem. Usually a k on the top of a fraction is better than a k on the bottom, so I'm not going to move it over, because if we move it over, it would appear down here and make things a little bit more complicated. Yeah. So next I'm going to try to solve this thing. Actually, before I solve it for L, I'm going to figure out what C is. Sometimes it's useful to find what C is before you go about the work of solving for the Y, or solving for the L, or solving for the whatever the dependent variable is. Just because it means you don't have to worry about moving this C around as you rearrange the equation. So the next thing I'm going to do is I'm going to plug in the initial condition. So if L of 1 is 1, that says, the L of 1 is negative 1, that says when T is 1, L is negative 1. So I'm plugging in T is 1, and L is negative 1. So on the left-hand side, I have negative 1 to the negative 1 over negative 1. We've got K. We've got 1 ln 1 minus 1 plus C. So negative 1 to the negative 1 is 1 over negative 1, which is negative 1 divided by negative 1 gives you 1 on the left-hand side. Ln of 1 is 0. This is just K times negative 1 plus C. This is basically a negative K, so C is the same thing as 1 plus K. Right, so using this initial condition, we have now figured out what C is. So our equation now is that L to the negative 1 over negative 1 equals K times T ln T minus T plus 1 plus K. And now we want to try to solve this thing for L. Solve it for the dependent variable. This is an example of an equation where we can get an explicit solution. We can, and the reason is because there's only one L in here. If there's only one of a variable appearing in there, it's usually easy to solve for that variable. So only one L, we can in fact solve for L. So the first thing we're going to do, if we're solving for L, is we're going to get rid of that negative 1 on the bottom, multiply both sides by negative 1. So L to negative 1 is really 1 over L. Here's negative K, T ln T minus T, plus 1 plus K. Oh, negative 1 multiplies here, negative 1 also multiplies here. So basically multiplying both sides by negative 1. And here we've got two terms here, so they both become negative. Next, I multiply both sides by L, then I move the L ups here, I divide both sides by this thing. So I'll get 1 over that whole thing, negative K, bracket T ln T minus T, minus 1 plus K, that whole thing equals L. So this is now the solution to the differential equation. Right? L of T is 1 over negative K T ln T minus T minus 1 plus K. You'll notice there's still, looks like there's two variables in here, right? There's still the T's, which is your independent variables, and also those K's, which is that constant. It turns out that there's a number of applied situations where there are sort of these constants in the differential equation that it's useful to keep in there until the very end. And the reason is because there's one differential equation that describes many different situations in the world. And if we keep the K in there, that situation, this solution will also describe all of those many different situations, and different values of K describe different situations.
Aren't IVP problems similar to bacterial growth populations?
Some of them are. So initial value problem is just any situation where we have a differential equation and an initial condition. But bacterial growth is one example of that. So bacterial growth problem usually, so for example, if you want to talk about bacterial growth one, right, the bacterial growth one is a, right, I said, it looks something like this, right? The rate growth of the population, some constant times the actual population. And this constant describes how many new bacteria are there for every old bacteria. And usually we have something like this, which says we started out with 100 of them, right? Now, this differential equation is nothing like this. This differential equation is a lot more complicated. So this situation is a lot more complicated than bacterial growth.
But in bacterial growth, we're still solving for C and then
Yes.
manipulating numbers.
Exactly. Exactly. So bacterial growth is sort of one example of this procedure. Yes. Yeah. Any other questions about this at this point? About sort of this algebraic procedure. Now, the other thing to mention about this guy here, this guy is an explicit solution. Right? It's not just an implicit solution. It actually has, well, it's not y here, it's L, but I actually have written L in terms of t. You don't have like an equation with both L's and T's. Like if it was like this would be an implicit solution. This guy is an explicit solution, because I can actually write it as L of t equals. And I will say, if I'm asking you to solve one of these things on the test, or am I asking for an implicit solution or for an explicit solution? I will specifically say, find an implicit solution to this, or find an explicit solution to this. Any other questions before I move on? Okay. The last thing I'm going to talk about are word problems. Basically, actually, how does this technique of separation of variables, how does it apply to actual problems in the real world? And there's ridiculously many different problems out there that can be solved in differential equations. I'm going to cover two different types in this section. The first type is going to be ones where I tell you what the differential equation is. All you have to really do is interpret the solution. The second type is a special type of problem called a mixing problem, which I'll talk about when it comes up. But the idea here is that what we're going to be doing is we're going to be solving word problems involving these sorts of differential equations, ones that are separable. So the first thing to mention is that some situations I'll tell you what the solution, what the differential equation is, and I'll ask you to solve it. But I'll also ask you to interpret what the solution represents. So sometimes this means nothing more than remembering what the variables represent. So sometimes all you really need to understand is, okay, the independent variable's population, the dependent variable's time. But sometimes you have to look at the graphs of the solutions and figure out what this graph represents in the real world. And if you're ever looking at the graphs of solutions, it's always going to be a graphing calculator thing. Pull out your graphing calculator, sketch the graph. I'm never going to ask you to graph these things without a graphing calculator. So here's an example from biology. Here we have a consumer which absorbs nutrients from its food. And then this is a differential equation which represents that. So x and y represent the nutrient content of the food and the consumer. So x is, how nutritious the food is. Y is how nutritious how much nutrients the thing that's eating the food has. This says dy dx is how fast the nutrient content of the consumer increases as the nutrient content of the food increases. So if you put, for example, say it's an amoeba and it's eating little bacteria, and if the bacteria are very nutritious bacteria, the amoeba is going to get more nutrients. Its nutrition level is going to increase. And that's what this represents. How fast is that nutrition level going to increase when we start increasing the nutrition level of its food? And the answer is going to depend upon the ratio between the nutrition in the amoeba and the nutrition in the bacteria. It's also going to have this 1 over theta in here. This theta is a constant which basically describes how efficient the thing is at absorbing food. So what we're going to do is they're going to ask us to solve this differential equation and sort of talk about what happens in two different situations. What happens when theta is 1 and what happens when theta goes to infinity. And interpret these two different solutions. So here we have dy over dx equals 1 over theta y over x. So again, I'm going to try to get all the y's on the left, all the x's on the right. So I'm going to now I'm also going to multiply both sides by theta. I'm going to move the theta over on the left here, and the reason is because that'll make it a constant on the top of a function is always better than a constant on the bottom. So on the left, I'll have theta dy over y. On the right, I'll have 1 over x dx. And then I put integral signs on both of those, and I integrate. This is basically a constant theta times 1 over y. So the antiderivative here will be theta times ln of the absolute value of y. Here, the integral of ln of x, or 1 over x, is ln of the absolute value of x. We add on the plus c. Let me rearrange this equation. So divide both sides by theta. So we have something like this. ln of the absolute value of y is ln of the absolute value of x plus c over theta. And then to get rid of the ln, we're going to put e to both sides. Now I can get rid of the absolute value of y situation because I'm assuming that y is never going to be negative. We're talking about nutrient contents of things. You can't really have a negative amount of nutrients. So we have something like this. Y equals e to the ln absolute value of x plus c over theta. And this is the explicit solution. So this is what we get for part A, right? I've solved the differential equation. I've found this formula for y in terms of x. So the next question sort of describe what happens in different situations. So the first situation they ask is what happens when theta equals 1? Well, if theta equals 1, we have this situation. We have y equals ln absolute value of x plus c over 1. E to that thing. Right? So we really have... Oh, I can get rid of these absolute value signs too, because x is also something that can't be negative. X is another amount of nutrients in the food. You can't have a negative amount of nutrients in there. So anything that can't be negative, you don't need those absolute value signs around. So this is really e to the ln x. Now ln x plus c means you can take e to the ln x times e to the c. E to the c is just x. So we have this situation. Y is e to the c times x. Now e to the c is just a constant, right? It's a complicated constant. It's e to the original constant, but it's still just a constant. So I'm going to call it k. So in this situation, when y is k times x, what that's saying is the nutrient content in the consumer, in the amoeba, is some constant times the nutrient content in the food. So it's saying that if you graph this thing, the graph is going to look like this, right? The k is going to determine how steep that graph is. But basically, and the x is the nutrients in food, and this is the nutrients in the consumer. So what's happening in this situation basically is that the amount of nutrients in the amoeba has is directly proportional to the amount of nutrients the bacteria has. Basically, it's basically representing something being 100% efficient at absorbing those nutrients, right? You know, if there's 0.2 grams of nutrients in the food, there'll be 0.2 grams in the amoeba. Or maybe there'll be 0.4 grams in the amoeba because it'll eat twice as much food as its own mass, or something like that. But the idea is there's a linear relationship here. So in the situation where theta is 1, we have a linear relationship between y and x. Right? So that's when it asks what happens when theta equals 1, we can say when theta equals 1, there is a linear relationship between y and x. Or we could say that y is directly proportional to x. It's another way of describing that situation. Now, if we look at this same situation, right, this is a solution I got down here. Y equals e to the ln x plus c over theta. Right, the next situation they want to describe is what happens as theta goes to infinity. Right, well, if theta goes to infinity, this whole thing is something over infinity, so that whole thing will become 0. So if theta goes to infinity, we have y equals e to the power of 0. Right, we have something over infinity. That something over infinity has got to be 0. So y equals 1 in this situation. So we can say something like, when theta goes to infinity, so what happens if you look at y equals 1 is you have a graph like this. Right? Here's the nutrient content in the food, here's the nutrient content in the consumer. And in this situation, basically, the nutrient content in the food does not even affect the nutrient content in the consumer, right? It's the same no matter what the nutrient content in the food is. So when theta goes to infinity, the nutrient content is constant. So this is a situation like, this is a very sort of very regulated situation. It's a situation in which, and this happens for a lot of, like, we do it fairly well for things like blood sugar. You know, that we, no matter how much sugar, now, if you're diabetic, this is very different, but most people who are non-diabetic, whose insulin-producing systems work well, your blood sugar won't change very much depending upon how much sugar you eat in your food. It'll change a little bit, but it won't change a lot, right? It'll be a situation like this. The nutrient content in the food doesn't really affect the nutrient content in your blood. Whereas for people who are diabetic, it's more like this situation. The more sugar you eat, the more, you know, it's this, if you eat like really, really sweet food, you're going to have hugely high blood sugar. So that makes sense, sort of the difference between these two situations. When theta is 1, we're talking about someone who's diabetic. When theta goes to infinity, we're talking about someone who has a really well-functioning regulation system. Now, this is not good. I was going to say, the other thing you mentioned about this is not a very good situation if 1 is a very low level of whatever nutrient we're talking about. Because then you're going to have a situation where no matter how much sugar you eat, you can never get your blood sugar high enough to actually function. Yeah. Any questions about this example?
Could we refer, like, if you were asking us to explain that situation, could we just say, you know, as the nutrient content goes to infinity, as the nutrients go to infinity, the nutrient content in the amoeba approaches 1?
Yes. Now the problem is that 1 here. Now the reason I say,
isn't it?
sorry.
Isn't it like I'm just kind of thinking horizontal asymptote just from the way.
Yeah, it's not quite, because the
No.
situation, what's going on here is you actually have 3 different variables.
Okay.
Right, so right. So if it was as x goes to infinity,
Yeah.
right? But the idea here is that theta is a variable which affects, it's called a parameter. It changes the shape of the graph.
Okay.
So different values of theta will, so if you go for like theta equals 2, you'll have something that's between this guy and this guy. You'll have something that looks somewhat like this. You know, it increases, but not linearly. It kind of flattens off.
Okay.
Yeah. Okay. So the other type of problem, a word problem that can come up from section 9.3 is what's called a mixing problem. And a mixing problem is one where you're going to have to set up the differential equation yourself, rather than it being like, here's the differential equation, solve it, interpret sort of what's going on here. You're going to have to set it up yourself. And in this situation, it's a situation where we have 2 different solutions mixing. So it can be 2 salt and water solutions. It could be carbon dioxide and air solutions. Solutions is in something dissolved in something else, a chemistry situation. And what you want to measure is, so oftentimes you have a situation like we've got salt water and we've got fresh water being poured into the salt water. And as the fresh water is being poured in, there'll be less and less and less salt in there. And we can describe this situation with a differential equation. We can describe what the rate of change of the amount of salt is in relationship to the amount of salt that's there. And we can set up this differential equation, we can solve it, and once we solve it, we'll have sort of a function which describes how this amount of salt changes. So in example 6 here, a situation where the air in the room has a volume of 180 meters cubed. It contains 0.15% carbon dioxide, but then new air is coming in which has a percentage of 0.05% carbon dioxide. And it flows in at a rate of 2 meters cubed per minute, and the mixed air flows out at the same rate. So we want to find the percentage of carbon dioxide in the room as a function of time. Well, what's usually actually easier in these sorts of problems is rather find. So what you want to do is you want to set up a differential equation which describes the rate of change of the amount of carbon dioxide in relationship to the amount of carbon dioxide there already is in there. So the first thing I'm going to say in all these problems, usually the easiest thing to work with is the amount of whatever the thing is we're talking about. So here A of t represents the amount of CO2 in liters, right? So what happens is there's two things going on that's going to change the amount of CO2 there is, right? There is air flowing into the room, and there's air flowing out of the room. So the amount of CO2 entering is, well, it flows in at cubic meters. It's not in liters. Sorry, the volume here is cubic meters. So it flows in at so that the air flows in at 2 cubic meters per minute. 0.05% of it is carbon dioxide. So the amount of CO2 entering is 2. Why did I have to say 5? I think it was a different problem. Anyways, I realize this is probably not the best mark for me to be writing with. 2 times 0.05%. So if we do that calculation, we get 0.001. This is the amount of CO2 flowing in per minute. 0.01 meters cubed of CO2 is flowing in per minute. If we want to figure out the amount of CO2 leaving, well, what we've got to do is we've got to take, right, so the idea is air is leaving, again, at 2 cubic meters per minute. But what we don't know is the percentage of CO2 in that air which is leaving. So if you want to find the amount leaving, you're going to have 2 times the percentage of CO2. Now, the percentage of CO2 is the amount of CO2 divided by the size of the room. Right? If you want to figure out how much of the room is CO2, you take the amount of CO2 divided by the size of the room. So it's going to be 2 times A of t over, where is it, 180. This is the percentage of CO2 in the room. This will be as a decimal, not as a percent, but the idea is the same thing. And so here, this simplifies to A of t over 90. So the amount of CO2 entering is 0.001. The amount of CO2 leaving is A of t over 90. And the idea is that means that we can figure out, we can describe this situation as a differential equation. A prime of t, now A prime of t is the rate of change of the amount of CO2. So the rate of change of the amount of CO2, that's going to equal 0.001, this is the amount of CO2 that's entering, minus A of t over 90. This is the amount of CO2 that's leaving. If you want to figure out how is the amount of CO2 changing, we've got to figure out how much is entering, subtract how much is leaving. So this number here is the amount entering. This number here is the amount leaving. And this is a differential equation. It's a description of how is the amount of CO2 changing in terms of how much CO2 is there in the room. Right? The idea is the more CO2 is in the room, the more CO2 is going to leave. That's going to mean the amount is going to decrease faster. So then what we've got to do is you've got to solve this differential equation. So I'm just going to write this as dA over dt equals 0.001 minus A over 90. I'm going to multiply both sides by 90 to make it simpler. So 90 dA, 0.001 times 90 is 0.09 minus A, this whole thing's times dt. Divide both sides by 0.09 minus a. I get 90 dA over 0.09 minus a equals dt. Then I can integrate both sides. If I integrate the left-hand side, 90 over, the 90 is going to be a constant, it's going to stay out front. The integral of 1 over 0.09 minus a is negative ln absolute value of 0.09 minus a. That negative sign is because there's a negative in front of the a inside there. If it was a minus 0.09, it would just be ln of a minus 0.09, but because basically I'm doing a chain rule here, there's a number in front of the variable, so I have to divide by that constant, which is negative 1, which puts that negative sign in front. And the integral of dt is t plus c. So now I'm going to solve this thing for t. So negative ln absolute value 0.09 minus a equals t plus c over 90. Actually, I move the negative over there. So 0.09 minus a is e to the t plus c over negative 90. Negative a is e to the t plus c over negative 90 minus 0.09. Multiply both sides by negative 1. A is negative e to the t plus c over negative 90 plus 0.09. That's the function which describes what the amount of carbon dioxide is over time. And if you graph this thing, this is what the picture is going to look like. Here's the level 0.09. If you graph this thing, you'll get something that looks like a graph that looks like that. It'll be an exponential graph which decreases towards 0.09. The idea is over time, as the air with lots of carbon dioxide it gets replaced with clean air, the amount of carbon dioxide is going to decrease towards this amount. And this amount turns out to be the amount that's in the air outside.
So is it their equilibrium?
Yes, this is also called an equilibrium solution, exactly. 0.09, yeah. So if you picked A equals, so if you picked, now here you'd have to pick C to be you have to pick C to basically be infinity. C is infinity. This thing will become negative infinity. E to the negative infinity will become 0. We'll get A equals 0.09. So yes, if you pick C to be infinity, you'll get that equilibrium solution. So if you answer this question, okay. So I guess I actually answered the second question first. So what happens in the long run? Well, what happens in the long run is the amount of carbon dioxide approaches 0.09. I didn't quite finish the first part because I didn't use this 0.15% up here. I didn't use this part that what happens at the beginning of the situation, what's called the initial condition. I did not use that initial condition. So I need to use that initial condition now to find the C here. So when t equals 0, A is, well, we've got 180 cubic meter room. We've got 0.15% of that is CO2. So if we take 180 times 0.15%, that gives you, I'm gonna pull up a calculator. One 180 times 0.0015, 0.27. So this is the amount we start with. So what I can do is I can take this equation, put in t equals 0, put in 0.27, figure out what C is. So 0.27 equals negative e to the t plus c over negative 90 plus 0.09. Oh, t is 0. Move the 0.09 over here. We get 0.18 is negative e to the 0 plus c over negative 90 multiplied by negative 1, negative, wait. I'm trying to figure out how this ends up being a negative number. Oh, I think I know what went on. Oh, great, I shouldn't have erased that. At one point, there was an ln of an absolute value of something. I got rid of those absolute value signs. I actually shouldn't have. And the reason is because what was inside those actual value signs was actually something that ended up being negative in this situation. So this will actually end up being a positive number when I get rid of those absolute value signs. It actually, if I got rid of those absolute signs, put a negative sign on it. So if you actually look back, and the step would have looked like this. Let me see if I can recreate it. Here we would have had 90 negative ln absolute value of 0.09 minus a. And when I rearranged this, I got t plus c over negative 90, and I had this. Now really what I should have done is I should have said the absolute value of this, because the amount of CO2 is bigger than 0.09. So the absolute value of this will actually be a minus 0.09. It won't be 0.09 minus a. The absolute value of it will be the positive version of it. And since a is going to be bigger than 0.09, it's going to look like this. And then if I rearrange it and do everything, I'll get the same thing but with a plus on the end. So these should be positive. So c over negative 90 equals ln of 0.18. So c is negative 90 ln 0.18. So that's what the constant is in this situation, which means that the amount of carbon dioxide is this thing, but with a negative 90 ln of 0.18 in where the c was. Right, this is the formula for the amount of carbon dioxide. So A of t equals that. And now here it actually doesn't ask you for the amount of carbon dioxide, it asks you for the percentage. If you want to find the percentage of something, we just take the amount and divide it by the size of the room or size of the container and multiply by 100. So we can divide this whole thing by the size of the container. Size of the container is 180. And multiply by 100. This is going to give you a formula for the percentage of carbon dioxide. Now it turns out that thing can simplify substantially. If you work with it, that thing will simplify a lot simpler than the way it's written right now. The reason is because if I could have t over negative 90, I could have this thing over negative 90. When I do this thing over negative 90, these negative 90s will cancel. Then I have e to the t over negative 90 plus e to the negative 0.18. ln 0.18 and e and the ln will cancel. So another version of this solution that you might see looks like this. Something like this, 0.18 e to the t over negative 90 plus 0.09 over 1.8. This is a simplified version of this formula for the percentage. I'm not going to require you to simplify it, so if you don't want to do the algebra simplify, you don't have to, but it will simplify to this. And if you look at the answer in the back of the book, you'll see something like this in there. But anyways, this is an example of this thing that's called a mixing problem, which describes how the quantities of things change over time.
There's a few of these to practice.
There's a few of these to practice in the book, exactly. There's about, if you include the even-numbered ones, there's about 5 or 6.
Okay.
If the odd-numbered ones, there's only 3 of them. But there's a bunch of these to practice in the book. We're going to be doing one as a group problem later on. So this stuff is still confusing you. I picked a slightly harder one to do as an example. The group problem one's easier than the example is. But yeah, this is the only situation I'm ever going to give you. We're going to have to come up with a differential equation and then solve it. Yeah. Any other questions about this? Okay, so I'm going to start. Actually, no, I'm going to give you the break now for 10 minutes. It's a little bit early for the break, but I'd rather do section 9.4 altogether. So I'll be doing section 9.4 after the break. So take 10 minutes, think about this stuff. I'm going to run upstairs and get the assignment number 4s. I'll be back with those in a few minutes. Yes, Dimitri?
Did we get the quizzes back?
Yes, I'll do that at the end of class today. Because I need to run up and get those assignments for everyone. So I'll do back the quiz at the end of class. Yeah.
I had stayed for one.
Oh wait, why not open the assignment? Just printed the assignment.
I'm trying to get into the team organic course, but I have a really tough time. So,
God, there was no math, it was just like theory.
So also I'm screwed because I didn't do math 12. I mean, you didn't do math 12, I did. Which was 5 years ago. Yeah, I'm like, oh, I said it kept
that was the same. That was the same with what I went. I think we can.
Okay, so I'm going to get started again. I'm sorry it took me a little bit longer than 10 minutes to go up, get those printed and come back. Mostly because I dropped my flash drive with the actual assignments on it when I went up there. Anyways, but for the next 40, 50 minutes or so, I'm going to be doing some models for population growth. I'm going to be covering section 9.4, and then after that, it'll just be group problems. So the idea, oh yes, sorry, question? The quizzes are here. I'm having them back at the end of class. Yes, I'm having them back at the end of class, as I said before. So yes, and that's just because I had to use the break to run up there, so I couldn't use the break to hand them back. So the idea of covering section 9.4 today is the idea that within section 9.4 is a bunch of different models for population growth, a bunch of different differential equations which describe how different sorts of populations grow. And the idea is this is mostly more examples of the type of stuff that we covered in section 9.3. It's more examples of different sorts of separable differential equations, different sorts of differential equations which we can solve using this method that I've been dealing with of separation of variables, where you can sort of see the relationship between what the differential equation looks like and what the solution looks like. And that's the idea here, is that this is the reason I'm doing these examples is because I want you to be able to see that relationship. What does the differential equation look like? How does that relate to what the solution looks like? So the first two models we're going to deal with are what are called the exponential model and the logistic model. The two most basic models of population growth. They're the most common ones. And they're ones in which you should definitely be able to see that relationship between the differential equation and the solution. So here's an example of a differential equation which fits into one of these models. This is a differential equation of the logistic model. Is there anyone here who has studied, I'm guessing, how many people here have seen exponential growth before? How many people have seen exponential growth using differential equations? Okay, a couple people. Anyways, if you've ever seen this thing, dp over dt equals kp, this is what's called the differential equation for exponential growth. How about logistic equations? How many people here have seen logistic equations before? Which logistic functions? Anyone? No. Anyways, okay. Logistic equations are sort of the next most complicated thing, and they happen in situations like this. I know some people who have seen them before in like non-calculus classes, but really before calculus, you can't actually, figure out where the equation comes from. So the first model I'm going to talk about is called the natural growth model or the exponential model. The idea is it's a situation like this one that I talked about way back, where you grew up a bacteria colony. In section 9.1, I talked about this differential equation, which says the rate of growth of the bacteria colony is the same as the number of bacteria, because each bacteria is going to have one daughter cell. Each bacteria is going to have one offspring, basically. Now, this is the description of bacterial growth. If it's not a bacteria colony, for something which reproduces differently, it might, but if it's a small population compared to the environment, it might still grow in the same way. In that the rate of population growth is only going to depend on one thing. It's going to depend upon the population. It's going to be some constant times the population. This basically describes situations where the number of offspring per individual is fixed. So where every couple has approximately 2.2 children, this is an example of exponential growth, or of natural growth, I guess at this point. dp over dt equals kp. Now if we have this equation, we can actually go about trying to solve that. Multiply both sides by dt. We get this. And divide both sides by p, Integrate both sides. Integral of this is ln absolute value of p. Integral of this is k times t plus c. The population is always positive, so we can get rid of those absolute value signs. Take the ln, put e to both sides. We get this, p equals e to the kt plus c. We can write this as e to the kt times e to the c. And e to the c is just some number. That number we actually call p0. So we get the population is p0 times e to the kt. That's a solution to this sort of differential equation. A differential equation where the population growth rate just depends upon how big the population is going to have a solution which looks like an exponential function times some constant. Or they sometimes call it capital C rather than P0 in that version down there. It turns out that capital C is equal to P0, which is one of the reasons I didn't say that before. But the idea is, if you graph all of these solutions, if you graph this thing for different values of P0, you will get graphs that look like this. They're all exponential functions. So you'll get things that grow exponentially. As the time increases, the population increases more and more and more rapidly. And the reason that happens is because the rate of population growth is proportional to the population. So the bigger the population gets, the bigger the rate of population growth gets. So that's basically the main feature of exponential growth, is that the larger the population gets, the steeper the graph gets. The faster and faster the population grows. As the population goes smaller, as you go towards this end of the graph, it flattens out. So this sort of differential equation leads to an exponential situation, which describes exponential growth. That's sort of the first example of a differential equation which describes population growth and what its solution looks like. Any questions about this solution before we move on to the next example? Okay. The next example is what's called the logistic growth model. And this is a more realistic situation because populations do not continue to grow exponentially. At some point, there's going to be a maximum population size. And this happens for a variety of reasons. It can happen because habitat's limited. So if you're growing bacteria in a petri dish, you'll have a situation where the bacteria reach the edge of the petri dish. They can't grow anymore. You can have a situation where food supplies are limited. And the idea is in any of the situations we have what's called a carrying capacity. Carrying capacity is the description of what's the maximum possible population that the environment can sustain. And when you're doing the logistic model, you assume that there's two different things which the population growth rate is determined by. It's determined by what the population is, but it's also determined by what percentage of the food supply or the habitat supply is left. So the larger the population gets, the less of the food supply is left, so the slower the population is going to grow. So that's what this thing represents. M is the maximum possible population. P is the actual population. So if the maximum population is 1,000, P is 500, this is 500 over 1,000, which is 1/2. 1 minus 1/2 represents a half. So half of the food supply is left. if the population is 900 and m is 1,000, 900 over 1,000 is 9/10. 1 minus 1/10. 9/10 is 1/10. There's 1/10 of the food supply left. The idea is that this 1 minus p over m in that differential equation, so in this equation, which is called the logistic equation, this is the percent of food supply or habitat or whatever it is that's limiting the population growth. That's the percent that's left there. Right? And in this sort of situation is another example of a separable equation. We can rearrange this equation to separate the variables, solve this differential equation, and see what we get. So when we do that, we're going to want to move the dt over here and the p in the 1 minus p over m to the left-hand side. So we'll get dp over p times 1 minus p over m equals k dt. Now we can put an integral sign on both sides. The left-hand side is easy to integrate. That just integrates to kt plus c. The right-hand side is going to be a lot more difficult to integrate. Right? To integrate this right-hand side, we're going to use partial fractions. And before we use partial fractions, I'm actually going to multiply top and bottom by m. It'll make it a little bit simpler. So we'll have m dp over p times m minus p. And the idea is what we want, we have this, m over p times m minus p, and we want to write it as something over p plus something over m minus p. Right? We want to use partial fractions in order to integrate it. So we multiply both sides by p times m minus p. We get m is a m minus p plus b times p. If we plug in p equals 0, we get m is a m, so a is 1. If we plug in p equals m, this will go away. We get m equals b times p equals m, so b equals 1. So really what we're trying to integrate here is 1 over p plus 1 over m minus p dp. And this is going to equal kt plus c. Right? So to solve a logistic equation like this, in order to actually integrate it, we need to use partial fraction decomposition. Any questions about the partial fraction decomposition before I erase it and continue with the integral? Okay. So when we integrate that 1 over p, that gives you ln of the absolute value of p, right? If we integrate 1 over m minus p, that'll give you negative ln absolute value of m minus p. B equals 1. Sorry, it's a curvy 1. It's supposed to be a 1. 1! Same with the a. They're both 1. Yeah. Thank you for asking, because it was written weirdly. Now we have ln of something minus ln of something else, using our laws of logarithms. That's this. Ln of absolute value of p over m minus p.
Why does minus?
Why does this become a minus?
Yeah.
Because you're integrating with respect to p.
Oh,
So we do
yeah,
substitution,
yeah. Got it,
u
got it.
equals m minus p. The du is going to be negative dp. Yeah. You're not integrating with respect to m, if that makes sense. So then we get rid of the ln. We'll have p over m minus p equals e to the kt plus c. Now we can get rid of the absolute value signs if we put a plus or minus on the other side. Now I'm going to write this as e to the c times e to the kt. Now, e to the c here is actually just a constant. And plus or minus is also just a constant. It's either plus or it's minus. So I'm going to call this a e to the kt. And again, I'm still trying to solve this thing for p. So what I'm actually no, I'll do it this way. So I'll multiply both sides by m minus p. So the right-hand side is a m e to the kt minus a p e to the kt. I'm going to move this over to the left-hand side. Actually, no, I'm going to do it the other way. Sorry. I'm not going to multiply. I'm going to flip both sides. M minus p over p equals 1 over a e to the kt. So m over p is just m over p. P over p is just 1. We have m over p over minus 1 is, now 1 over a e to the kt is the same thing as 1 over a e to the negative kt. And that 1 over a I might as well call a2. Again, it's just a constant. It's a different constant, but still just a constant. So m over p is a2 e to the negative kt plus 1. Flip it both sides again. P over m is 1 over a2 e, 1 over 1 plus a2 e to the negative kt. Multiply both sides by m. I get this. P is m over 1 plus a2 e to the negative kt. Now the thing to mention about this procedure, this algebraic procedure I used to solve this equation for p, I'm not going to require that you replicate this procedure when you're dealing with logistic equations. The logistic growth model, what I'm going to expect you to do is to actually just use this formula here, which is the solution that I got there from solving that equation. P of t equals m over 1 plus e to the negative kt. And the other thing to mention is there's a formula for what this a represents. Here I call it a2, you could also just call it a. That a is always m minus p0 over p0, where p0 is the starting population. So these two formulas will be on the formula sheet on your test. So this procedure that I use to solve a logistic equation is not going to be something you need to know for the test. For the written assignment I just handed out, there is another equation which is similar to the logistic equation which I am asking you to solve. So I do want you to be able to go through this procedure at least once. But it's in a written assignment situation rather than a test situation, so you can sort of refer back to your notes when you're doing it. I'm not going to ask you to be able to come up with this position from scratch. What else are we going to mention about that? Oh yeah, also this whole thing is in the textbook too. This procedure of solving the logistic equation using exactly the same steps I did. So if it's confusing you, that's another place to look. Now the idea is, one thing I want to mention about this, if you graph these different solutions to the logistic equation, they will look like this. Here is the number m. M represents the maximum population. If you graph solutions to the logistic equation, their graphs will look like this. Curves that go up and they, oh boy, these are badly drawn graphs. Every single one of these curves will have a horizontal asymptote at m. And if you go to the left, they'll have a horizontal asymptote at 0. The idea is that any population situation which results in limited growth will always grow towards this carrying capacity, but it'll never get past the carrying capacity. Because you can't have a population higher than this. So population growth will slow down and slow down and slow down. And almost hit it, but not quite. If you look at this situation, as t goes to infinity, this thing becomes negative infinity. Sorry, this thing becomes negative infinity. E to the negative infinity becomes 0, so we have m over 1. And that's why all these things approach m. So no matter what a2 is, all these solutions will approach that maximum population m. there are also solutions that are up here that look like that. So if you start with a population beyond the carrying capacity, it'll die off until it reaches the carrying capacity. And that'll happen if A is a negative number. Yes, Dimitri?
What's that kind of graph called?
This? Logistic. Yeah. It's called a logistic function. Yeah. So the differential equation, this guy here is called the logistic equation. This is called the logistic function. Yeah. Any questions about this logistic function at this point? So again, to mention, all three of these formulas are on the formula sheet. So if I ask you any questions about logistic functions, always just turn to your formula sheet, refer to these three formulas, and try to use them. Oh yeah, note that solutions to logistic equation either grow towards the carrying capacity or shrink towards the carrying capacity. If you start with a population down here, it's going to grow and not exceed the carrying capacity. If you start with a population above it, it's going to die off until it reaches the carrying capacity. So we can apply the logistic model to various situations. When we do, we can just use the formulas that will be on your formula sheet, those ones from the previous slide. So here, example 1, we have a population which satisfies this differential equation with this initial condition. So the first thing we ask is, what is the carrying capacity? Well, the carrying capacity is that number m. And to see what the carrying capacity is, we're going to have to rearrange this equation to figure out what m is. So here we have dp over dt is 0.4p minus 0.001p squared. Well, what I'm going to do here is I'm going to take this 0.4p. So if you remember, the logistic equation looks like this. dp over dt is kp times 1 minus p over m. So to get a logistic equation, I need to have a 1 here. So what I'm going to do is I'm going to factor out something that will make this first term a 1. So I'm going to factor out a 0.4p out of both sides. So when I do that, I get dp over dt, sorry, not out of both sides, out of both terms on the right-hand side, 0.4t. 1 is left in the first term. If I divide 0.001 by 0.4, I get 0.025, I think. 0, yeah. There we go. Now this thing, 0.0025p, that can be written as p over 400. So, the carrying capacity, that m, is 400. So that's the answer to A. B, they want to ask what p prime of 0 is. Well, this equation says dp over dt is 0.4p minus 0.01p squared. So if I want to find p prime of 0, I can take 0.4 times p of 0 minus 0.01 times p of 0 squared. This differential equation will be true no matter what time we're talking about. So it'll be true at time 0. P of 0 is 50, so this will be 0.4 times 50 minus 0.001 times 50 squared. 0.4 times 50 is 20. Yeah. 50 squared is 2,500. 0.001 times 2,500 is 2.5. 20 minus 2.5 is 17.5. So that's what p prime of 0 is. Now for part C, it asks, when will the population reach 50% of the carrying capacity? Well, the idea is if we want to ask when the population will do something, we need to know what the solution is to this differential equation. What is the formula that represents the population? Well, the formula is this. M over 1 plus A e to the negative kt. Right? That's the formula for the population. The M here is 400. The K is 0.4. And the only thing we don't know is the A. And to find the A, we're going to use the M minus P0 over P0 formula. A is M minus P0 over P0, which is 400 minus 50 over 400. 400 minus 50 is 350. 350 over 400, and that reduces to 7/8.
What would be 50 over 50?
Oh. Oh yeah, thank you. I'm spacing, thank you. 350 over 50, which gives you 7. So this is a 7 there. So that is the formula that represents what the population is going to be. Now we want to know when it reaches 50% of the carrying capacity. The carrying capacity is 400. So 50% of the carrying capacity is 200. So we want this. 200 is 400 over 1 plus 7 e to the negative 0.4 t. Multiply both sides by that denominator. We have 200 times 1 plus 7 e to the negative 0.4 t is 400. Divide both sides by 200. 1 plus 7 e to the negative 0.4 t is 200. Subtract 1. 7 e to the negative 0.4 t is 199. 199 divided by 7 is 28.42. So e to the negative 0.4 t is 28.42. So negative 0.4 t is, just make sure that's, something's wrong here, because, 2. Not 200. 400 divided by 200 is 2. So this is 1 when I subtract from both sides. So this is 1/7. So this is ln of 1/7. So ln of 1, and so then t is ln 1/7 over negative 0.4, which is approximately ln 1 over 7 divided by 0.4 by negative 0.4 is 4.86. So we could say something like the population will reach 50% of the carrying capacity after 4.86. I think it's months in this situation. I can't remember. Anyways, from when I copied this from the textbook, I abbreviated it to save space, but I can't remember what the units are here. I think the units are months. 50% of the carrying capacity. Oh, years. 4.86 years. So after 4.86 years, the population will be 50% of the carrying capacity. Any questions about example C here? Okay. So again, any of these questions involved in the logistic model should be able to be fairly easily solved with these 3 equations here that's on that slide that are on the formula sheet. What I'm going to cover for the next 15-20 minutes are some examples of other population growth models. So some examples of other different ways of describing population growth that are more complicated than the logistic model. And again, in any of these other situations, I will tell you what the differential equation is, but you might still have to solve it on your own and figure out what the solution looks like. So there's two examples I'm going to do here. One is called the doomsday equation. The other one is called the Gompertz model. They're two examples from the textbook. There are many other examples in the textbook. Take a look at them and try to see if you can solve all those equations and interpret what the solution represents. But the key thing here is going to be able to take a differential equation, solve it, and interpret what that solution represents in terms of population growth. Again, population growth is an easier situation to interpret solutions than the ones that I did earlier this class, where I had that one with the theta in it, where the nutritional value of the producer in the food, or the consumer in the food. These ones are going to be a little bit easier to interpret than that, but the same sorts of problems. So here is the doomsday equation. It looks like dy over dt equals ky to the 1 plus c. So the first thing they want you to do is to solve the differential equation. Determine the solution which satisfies that initial condition, y of 0 equals y0. So dy over dt is ky to the 1 plus c. So again, I'm going to separate variables, move all the y's to the left, all the t's to the right. So I get dy over y to the 1 plus c equals k dt. Y to the 1 plus c is the same thing, sorry, 1 over y to the 1 plus c is the same thing as y to the negative 1 minus c. We integrate an exponent, we add 1 to the exponent, divide by the new exponent. Add 1 to this thing, it becomes y to the negative c, divide by the new exponent, we divide by negative c. So here we have y to the negative c over negative c, and here I get kt plus, I'm going to call it a. I'm trying to find something because lowercase c and capital C are very difficult to tell the difference between. So I get kt plus a there. So now what I want to do is I want to solve this equation. So y to the negative c is negative c times kt plus a. Now y to the negative c is the same thing as 1 over y to the c. So here it'll be negative ct minus ca. So I multiply both sides by y to the c, divide both sides by this thing. So I'll get a y to the c over here. I will get 1 over negative ct minus, now ca I'm just going to call b. Again, ca is just a constant. I might as well just call it b. And if I want to solve this thing for y, I've got to take the cth root of both sides. I'll get rid of this c. So y is the cth root of 1 over negative ct minus b. So this is, then the other thing I need to do is I need to say, okay, y of 0 equals y0. So when t is 0, y is y0. So I plug in t equals 0. I will have y0 equals the cth root of 1 over, this part goes away, negative b. So, to get rid of the cth root, I'm going to take the cth power of both sides. So y0 to the c is 1 over negative b. Negative b is 1 over y0 to the c. So b is negative 1 over y0 to the c. So that means the solution is that y of t, y as a function of t, is the cth root of 1 over negative ct. and negative b is plus 1 over y0 to the power of c. So that's what this final solution is going to look like. So that's the answer for part A. I solved that differential equation by the formula for y in terms of c. Now you notice again there's still some constants in here. There's that constant c in there, there's a constant k in there, there's a constant y0 in there. That's okay. So part B asks you to show that there's some finite time, capital T, such that if lowercase t approaches that finite time, our solution is going to go to infinity. Right? That's what part B asks us to do, is to show that there is some time, capital T, such that solution as t approaches that time goes to infinity. Well, if something goes to infinity, that means there's a vertical asymptote there. If there's a vertical asymptote there, that means that this denominator has to equal 0 for there to be a vertical asymptote. Right? So let's see what happens if I take this thing and set it equal to 0. Well, I can move the negative ckT to the other side. So I get 1 over y0 to the c equals ckT. Divide both sides by ck. I get t equals 1 over ck y0 to the c. So capital T is this guy. And if you take the limit as t goes to this thing, what we're going to do is we're going to plug this thing into the equation. If you plug this thing into the equation, ck times this thing is 1 over y0 to the c. That means this denominator goes to 0, so the whole thing goes to infinity. So to write that out, I'm going to write it out this way. As t approaches 1 over ck y0 to the c, so if t approaches that thing, that capital T, negative ckT is going to approach 1 over y0 to the c. So I was going to approach negative 1 over y0 to the c. So negative ckT plus 1 over y0 to the c approaches 0. So 1 over this thing approaches infinity. So the cth root of 1 over that thing approaches infinity. So this is what the solution to this doomsday equation looks like. And I've shown you that there is some time, capital T, such that if time approaches that number, this thing, which represents the population, is actually going to go to infinity. So C is going to deal with a specific situation of this. So the reason this is called the doomsday equation is because there's this time at which the population goes to infinity. C deals with the situation, in this situation, a specific situation of this. I'm sorry, I didn't sleep very well last night, so I've been extra confused today, and therefore probably being confusing to you as well. So here we have a situation where we have a especially prolific breed of rabbits, and their differential equation looks like this. Y prime equals my to the 1.01. So this is basically telling you, so if you look at this equation, it's telling you that the k is capital M and the c is 0.01. So here basically I'm saying the k is capital M and the c is 0.01. And the other thing it's telling you is they start with 2 such rabbits. So the initial population is 2. And the question is, when is doomsday? How long is it going to be before these 2 rabbits grow to be an infinitely large population? Now, of course, this is not a very good model of any real situation because infinitely large population is not possible. However, there are organisms out there that grow faster, like they grow at populations fast enough that they become almost infinite. So they become a real problem and they basically use up all the food supply, is the idea. And so this is sort of, this breed of rabbits can be modeled using this situation. The question is, how long do we have before they eat up all the food available? Well, this is the formula for doomsday. So I'm just going to take, right, capital T is this time that's called doomsday. And I'm going to take all these numbers I found and plug them into that formula. So I have 1 over 0.01 times m times 2 to the 0.01. So I get basically 99.3 over m. So doomsday happens at time 99.3 over m.
We're gonna do this in our final exam or in test coming.
Perhaps. Now, likely it will be a little bit easier than this. Likely I give you a little bit. I probably give you this with a specific value of k, like 2 times, and a specific value of c. So if I was giving you this on the test, I'd give it to you with like dy over dt equals 2y to the 1.01 or something like that. And I'd ask you solve the differential equation, show that it has a vertical asymptote, show that your solution has a vertical asymptote. Now, the other thing to mention, this thing I can graph, right? If I actually graph, the other thing too, of course, is in this situation, because my solution here has all these constants in it, I can't actually graph it. But if I actually picked a situation where I knew what all these numbers were, it was something I could graph. And if I graphed it, I could see that it has a vertical asymptote. So if something like this was going to come up in the test, the k would be a specific number, the c would be a specific number, and I'd ask you to first solve the differential equation. Second part, show that this solution has a vertical asymptote, right? Which you can do with your graphing calculator, right? Again, this one is particularly hard because of these constants. You can't do this with a graphing calculator. But if you knew what c was, you knew what k was, you knew what y0 was, this is something you can just type in your graphing calculator, look at the graph. Say, okay, this graph is a vertical asymptote. This vertical asymptote represents a situation where the number of rabbits grows infinitely large. That's the idea. So yeah, again, the annoying thing about the way the questions are set up in the book is there aren't a lot of these questions in the book have all these constants floating around, which makes the questions harder than they need to be.
Can't you just pick arbitrary constants just
Yes.
to be able to pass it? That's
Exactly.
what I would do.
No, exactly. And this is now the reason I don't. If you're looking at the ones in the book, yes, picking arbitrary constants, plugging them into your graphing calculator is a great way of studying these things. The annoying thing is that none of the that for questions to have the same answer for everyone, I have to say what those constants are.
Right.
So one of the things that will go on is if you actually look at I'm trying to think if I did this on a practice test. No, I did it on the written assignment. You notice at one point I said pick 5 values for the constant and sketch the graph for each of those 5 values. There is some situations where I'm actually asking you to do arbitrary constants. And that's something the book doesn't ask you to do because the book wants to have a single answer that everyone will get. And same thing with WebAssign. They always want you to have a single answer. But in general, yes, you can pick arbitrary constants and sketch the graph of all those, and that will allow you to sort of understand what this family of solutions looks like. Because unlike this with all these constants in it, this is what's called a family of solutions. Any other questions about this example? Okay, so the last example is called the Gompertz model. Hopefully this one should be a little bit more straightforward. I mean, they're all kind of, because all these questions that are actually in the book have these weird values here, like they don't, like the C's and the M's and stuff like that. C is going to be one where they actually tell you what the numbers are, so you can actually graph it. But in general, they tend to have all these C's floating around, so they're harder to solve. If I give you anything on the test, they won't have all those constants floating around. At least not nearly as many. So, here the differential equation is dp over dt equals c ln m over p times p. So, the idea is we want to separate the variables and integrate this guy. So, So I'm going to multiply both sides by dt. Actually, first before I do that, I'm going to simplify that ln m over p is the same thing as ln m minus ln p. Divide both sides by that thing, we have dp over ln m minus ln p times p equals c dt. And then we can put an integral sign on both sides. Now when we integrate the left-hand side, now this is the reason I want to do this example, because this one's a little bit harder to integrate. This is one to integrate it, we're going to need to use substitution. We're going to need to make this whole thing here, the ln m minus ln p, just into a u. Substitution we're going to use is u equals ln m minus ln p.
Is it minus ln m?
No, there was no minus here.
It just looks like
That was a mistake on my part. Yeah. So derivative of ln m is just a constant, so this derivative is 0. Derivative of negative ln p is 1 over p dp. And look here, I have a dp over p, which is basically going to be a negative du. So the left-hand side will become integral of negative du over u. The right-hand side will integrate to ct plus, and I'm going to use capital A here rather than capital C, so I don't confuse my capital C's and my lowercase c's. Integrating this guy gives you negative ln absolute value of u, and we know what u is. U is ln m minus ln p. So now we've got to solve this thing for p. So first multiply both sides by negative 1. Negative ct minus a. Get rid of the ln on this side and add an e on the other side. When I get rid of this absolute value sign, I will get a plus or minus. This thing will become plus or minus e to the negative a, e to the negative ct, and this plus or minus e to the negative a is just another constant I can call b. So here I have ln m minus ln p equals b e to the negative ct. I'm going to move the b to the negative ct over here, the ln p over here. So I have ln m minus b e to the negative ct equals ln p. Put e to both sides. So I have e to the ln m minus b e to the negative ct equals p. So there we go. That's my solution. E to the ln m minus b e to the negative ct. I've solved that equation for p. So the next thing, so that's part A. This is the answer for part A. This is, I've solved the differential equation. So the next step is to integrate both sides. No, it's not integrate both sides. What am I doing? Talking about the limit as t goes to infinity. So for part B, we're talking about what happens as t goes to infinity. Well, as t goes to infinity, e to the negative ct, that whole thing is going to go to 0. Because t is going to go to infinity, so negative ct is going to be a negative number. Or going to go negative infinity, e to the negative infinity goes to 0. Which means ln m minus b e to the negative ct, that whole thing goes to ln m. Right? So this whole thing in the exponent, this part's going to go to 0, and that whole thing will just go to ln m. So we will have e to the ln m. So the population approaches e to the ln m. E to the ln m is just m. So to sort of understand what these functions look like, we want to graph one of them. And so for part C, we're going to graph one with specific values of m, p0, and c. So for part C, m is 1,000, p0 is 100, c equals 0.05. So the solution looks like p equals ln 1,000 minus e to the ln 1,000 minus b e to the negative 0.05 t. So p0 is saying when t is 0, p is 100. So p0 means a population when time is 0. So we take the time as 0, we plug it in. We have 100 equals e to the ln 1,000 minus b times e to the 0. We take ln of both sides. ln of 100 equals ln of 1,000 minus b. And so b is ln of 1,000 minus ln of 100. So now, knowing what that constant b is, we can actually graph this thing. Actually, this thing, sorry, let me just simplify this. This is ln of 1,000 over 100, which is ln 10. So if we want to graph this guy, foo plot, so it looks like e to the power of ln m, which is ln 1,000, actually I might put the 1,000 brackets here, minus b, which is ln 10, e to the negative c is 0.05 t. So that's, let's put times here. There we go. So now I've graphed it. Now you'll see it doesn't, I can't see it. Okay, there I go, I've zoomed it out, but you can see it looks like a straight line, so maybe I need to zoom in like this on it. Uh-oh. Oh, I need to call it x rather than t. That's the reason it's not graphing. There we go. So now hopefully if I zoom out far enough, I'll see the graph. There it is. Okay, you can sort of see the graph there. There we go. There we go. Zoom out. There we go. So that's what the graph looks like of this guy. You'll notice it looks very similar to those logistic curves that I talked about before. It's describing basically the same situation. It's describing a situation where a population grows faster as a population increases until it gets close to a carrying capacity. And once it starts getting close to 1,000, population growth slows off dramatically and levels out. And that's because it's reaching that carrying capacity, it's reaching that maximum possible population.